Hey guys, welcome to 5.3a, which is the third video in chapter 5. We're going to be analyzing graphs of polynomial functions, and we're also going to be graphing cubic functions. So the first problem here is we need to learn some new terminology. We have the local max and the local min. These we like to think of as hills and valleys. So that is a local max is a hill. And then a local min is going to be a valley. What this looks like is as a graph curves up, this would be a local maximum because it's the highest point, and it can continue on, just kind of an example. And then a local min is when a graph dips down, like this. We call these turning points because it's where the graph changes from going up to down or changes from going down to up. So we still want to look at end behavior. Don't worry about this terminology. This is just as x approaches positive infinity, negative infinity, that just means as x goes to the right or as x goes to the left. And then f of x is like saying as y goes to the right y goes up or y goes down. We still look at the leading coefficient and the exponent. Now, turning points, like I said, that's where it's changing direction in a sense. If the degree is n, then there are at most n minus 1 turning points. So basically, let's say we had a degree of 5. So let's say it's a 5th degree polynomial. What we do is we recognize, so let me give you an example of the 5th degree, x to the 5th plus 4x squared plus 2. That's an example. So we look at the highest degree, 5, and then we just plug it in for n. So 5 minus 1 would equal 4. So there's 4 turning points for a polynomial like that. All right, we're going to keep going here. First example when we're graphing. So for the graph, we want to estimate the x-intercepts, any local maximum or minimums from the graph. Then we want to give the lowest degree of the polynomial possible. So the way that we do this is start by finding the x-intercepts. I'm going to write those over here. The x-intercepts, and then we'll just list them. So these are the coordinates where x crosses, or our graph crosses the x-axis. Excuse me. We have a point right here, point right here, one right here, here, and here. 5 different locations. Now, if we're estimating, these are all going to be some point and then 0 for the y value. The first one on the farthest left, this one right here, that looks like it's a little past negative 2. So we're going to say negative 2.10. The next one, this point here, again, looks like it's a little bit past the negative 1. So we could say negative 1 or negative 1.2. I'm not super picky. Just do the best that you can. This one in the middle looks like it's going right through 0. So 0, 0. Next one, looks like it's a little past 1. So let's say 1.10. And then lastly, this point here again looks like it's past the 2 mark. So we're going to say 2.10. We're not trying to be super exact here. We're just doing the best that we can. Then after we do the x-intercepts, we want to do local maxes and local mins. So I'm just going to say max, then minimum. Now, when we're talking about maxes and mins, we're just looking at the y values for these. We're not even thinking of them as like a coordinate. We just want to list the y values, since y is the only thing that goes up and down. So we have 2 local maxes here. It's possible to have more than one at a time. In the first one, this one right here, that looks like it's almost exactly at 3. So the y value there is 3. And then the y value over here on the second one, this one right here, looks like it's, I'd say it's halfway between 1 and 2. So we're going to say 1.5. And then the minimums, which is this one here and this one down here, that one looks like it's about negative 1.5. And this one looks like it's just shy of that 3 marks. We're going to say negative 2.9. But if you put negative 3, that's fine. Now the turning points are the number of times we change direction. So it's actually the number of mins and maxes. I circled 4 different points, so we have 4 turning points. Which makes sense because if you think about it, we have 1, 2, 3, 4, 5 solutions. And if it's 5 solutions, we would expect this to be a 5th degree polynomial. So that's what we're going to say here. And if you recall, the turning points is equal to the degree minus 1. So if we have a 5th degree, 5 minus 1 is 4. So that's why we have 4 turning points. Let's go back over to this one here. Okay, so again, we'll do the same thing. We will do x-intercepts, and we'll write the whole coordinate. Looks like we go exactly through -2, 0. There's only one x-intercept here, which is fine. And then the turning points we have, well, sorry, I should do max, min. For the maximum, we just have one of those. And then for the min, we also just have one. So we have this point here, this point here. So the max looks like it's right at 2, and the min looks like it's a little underneath. Oh, wait, we're counting by 2s here. Got to be careful. That's my bad. Since we're counting by 2s, technically this would be 4. So the maximum of 4, and then a minimum of slightly under 2. So we're going to say, I don't know, 1.9. Now I circled 2 different points for my max and min, which means we have 2 turning points. So the lowest possible degree has got to be 1 up from 2. So that's 3rd degree. Or you can just put 3. But. All right, let's keep going. Why does it keep doing that? All right, we want to use our graphing calculator for this one. So let me pull that up. We go to that y equals, and we type out this equation. Hopefully we're getting decent with typing out. Okay, then we graph that. It looks like we touch a few times, and this graph does match the diagram that we have on our paper. So use your graphing calculator to calculate the zeros of the polynomial and any local maximums or local minimums. So let's say x-intercepts, which are the zeros. Now you could just say x equals because the answers here are pretty nice. It looks like if we poke the graph here, we do go right through, it looks like it's at -0.5 or -1/2. And then another one here that we're going to just estimate. Looks like it's 1.8, right about there. And then the last one, 3.7 looks to be the x value. All right, we're just trying to do the best that we can. We're not going to be super exact because these are actually going to be more specific decimals. So just do the best you can there. And then the maximum and minimums. So max, min. We're again going to go to our calculator and try to get to that top point because that's going to be our maximum. It's kind of hard. Just do the best that you can. Looks like, now remember, we're looking for the y value here. 3.875. Or you could just round to 3.9. Let's just do that. And then we want to look at the minimum, the valley down here. And that looks like -3.1 if we round up, because it looks like -3.06, so we'd round up to -3.1. All right, continuing on. Come on. Why won't you let me move here? I'm having issues, sorry. Come on. Okay, let me just back up for a second. I apologize, just skipped with the part that you need to. All right, here we go. Now it seems to be working. All right, example 3. If you have a 4th degree polynomial and you're given one imaginary root, what is the maximum number of real roots? For this one here, 4th degree, and we know for sure we have one imaginary root. Be careful, because remember the rule. If you have one, it has to have a partner. So that means there's at least 2 imaginary roots. So the maximum number of real roots is actually only 2 real roots possible. Number 4, sketch a graph of a polynomial function that has 3 roots where one of them is a real root. Okay, this is the same thing as x approaches infinity, f of x goes down. That's the same thing as x goes to the right, y goes down. And then the other side is the same thing as saying as x goes to the left, y goes up. So thinking about that, as x goes to the right, y goes down. It's going to look like that. And as x goes to the left, y goes up. It's going to look like that. So this is definitely going to be an odd function, which we would expect since it has 3 roots. One of them has a real root. So if only one of them is a real root, the thing you have to think about here is how many times on a graph is it going to touch the x-axis. Imaginary numbers do not touch the x-axis, so if it's one real root, it's got to look something like this, where it only touches the x-axis once. It could also look like this. Something along those lines. We have no idea exactly where it's going to touch. This is just a general equation, but you just have to show the proper end behavior, and then it only goes through the x-axis once. Now example 5, same idea here. Sketch a graph of a polynomial function that has 2 roots where none of them are real. And then this says as x goes to the right, f of x goes up, so y goes up, x goes left, y also goes up. So this time we're going up and up, which looks like this. Don't worry, and you won't see this kind of notation for your test. It'll be in the usual notation. How would we have a graph where none of them are real? Meaning we can't touch the x-axis. So basically you just got to put it above the x-axis like this, and there's your answer. All right, continuing on, we have 2 more ideas. This last part here is usually its own lesson, but we just decided to turn it into one, save some time. Writing cubic functions. So for a cubic function, we know cubics are 3rd degree, so there's 3 solutions. Every time we're going to see 3 points that touch the x-axis. Those are our zeros. So the first one, this is -3, this point right here. This point here is -1, and this point is +3. If those are roots, we use the trick that we did before. But we don't know what the a value is. That's something new that we have to think about. The a value is what we're going to find after. This is how our cubic functions are always going to look. It's going to be a, and then it's going to be 3 sets of parentheses. So the first one we know has got to be x plus 3, because -3 was a solution. And then -1 is a solution, so we have the opposite, x plus 1. And lastly, we have 3, so it's got to be x minus 3. To find the a value, what we have to do is use this point right here, because that's the only point that isn't on the x-axis. What we're going to do with that is we're going to plug that point in for x and y in what we have so far. So the coordinate right there is -2, 1. So we're going to plug in -2 in all of our x values. And then we're going to plug in 1 for f of x, because that's technically y. It's going to be 1 equals a times -2 plus 3, -2 plus 1, and -2 minus 3. So the left side stays the same. 1 equals a times these two make 1, these two make -1, and these two make -5. So now what we're going to get when we multiply that out is 1 equals 5a, because you have two negatives, -1 times -5. Then to solve for a, we divide by 5, and we get a equals 1/5. Now that we have that, we go back to our original equation, which is this part up here, and then we just replace a with 1/5. 1/5, and then we just write the factors. X plus 3, x plus 1, and x minus 3. There's our answers there. And then for the last one, we're going to do the exact same thing. Identify the zeros. Sometimes they're given to us on a graph. Sometimes they're just going to be given to us in coordinate form. So here's 1, 2, 3 zeros. So we start with f of x equals a. It's always going to be like that. And then we do the parentheses. First one's going to be x plus 1, because this is -1. This is 2, and this is 4. So the opposite of -1 is +1. The opposite of +2 is x minus 2. And the opposite of 4 is x minus 4. And then we're always going to have at least one point that doesn't touch the x-axis, which is this point right here. That is 0, 4. So for our f of x, we get 4, because that's the y value. For a, we put 0. And then we have all of these right here. Oh, sorry, not for the a value. I was like, wait, that doesn't make sense. A is not 0. A is what we're solving for. X is 0. So 0 plus 1, 0 minus 2, and 0 minus 4. Now we're going to solve. So we get 4 equals a, 0 plus 1 is 1, 0 minus 2 is -2, and 0 minus 4 is -4. And then we just multiply everything out. So 4 equals, these two here are going to make 8a. We divide by 8. We get a equals 1/2. We're going to get fractions a lot, so don't feel bad if you get a fraction. Last answer is going to be f of x equals, oh, I must have erased something here. 1/2 x plus 1, x minus 2, and x minus 4. We'll do some more practice with these in class, so don't worry too much if you're struggling with these, since we didn't do very many examples. But basically, again, it's always going to be 3 solutions. You're going to have one point that isn't on the x-axis, and then you just got to plug that point in to solve for a. All right, go ahead and submit these out.